In today's video, we will learn about rotational equilibrium using this mechanical balance that you can see. In order to understand the rotational equilibrium, we first need to look at the concept of torque. Torque is a measure of how much a force causes an object to rotate around a point. It is defined as a product of force and momentum, whereas a momentum is a distance between the pivot point and the point where the force is applied. Torque is measured in Newton meters. Now, as we know what torque is, let's look at the definition of equilibrium. Equilibrium is a state where the sum of all torques acting on an object is zero. Let's try to understand the concept of rotational equilibrium with the help of this mechanical balance. This mechanical balance consists of a beam which has a distance scale on it. So here it's the distance scale. Under this beam there are hooks at an equally spaced distances where you can place the weights. These are the weights. Each weight piece has a mass of 20 grams, which means that each weight can exert a force of about 0.2 Newton, assuming that acceleration due to gravity is 10 meters per second square. Because we know that force is mass times the acceleration. So if we convert 20 gram mass into kilogram, it would be 0.02 kg, and if we multiply it with 10 meters per second square, which is acceleration due to gravity, so we will arrive at a value of 0.2 Newton, which each weight can exert. At present, the balance scale is in equilibrium position since no torque is acting either on the left hand side or on the right hand side. Now take the left hand side and place the weight at this point, which is about 14.5 centimeter away from the pivot point. So let's place the weight here. So as soon as the weight is placed, the balance is tipped downwards and attained a new equilibrium position. Now if we place another weight at 14.5 centimeter away on the right hand side, the beam will balance again and restore its original equilibrium position. So you can see that the beam has restored its original equilibrium position since the torque on both sides is balanced again. Let's now try to calculate the torque on both sides. So if we take the left hand side and we really find out that the force exerted by this weight is about 0.2 Newton, and also this weight is placed at a distance of 14.5 centimeter from this pivot point, which is the momentum. And as we know that the torque is force times the momentum, so we will multiply 0.2 Newton multiply by 0.145 meter or 14.5 centimeter. So we will get to know that the torque on the left hand side is 0.029, and we will give it a minus sign because it's being placed on the left hand side. And by the same logic, we can calculate the torque on the right hand side, which would also be 0.029 Newton meter, mainly because this weight is placed at a distance of about 14.5 centimeter to the right on this pivot point. So if we add both torque, it will cancel each other, which means that the net torque acting on this balance is zero. Now if we place another weight at this point at about 11.5 centimeter from this pivot point, let's see what happens. As you can see that the torque on the left hand side gets bigger, and therefore the balance is tipped towards the left hand side to attain a new equilibrium position. To balance that once again, so we will place another weight on the right hand side at a distance of about 11.5 centimeter. So now you can see the torque on both sides are equal but in opposite direction, therefore the net torque acting on this beam is once again zero. Now let's take another case in which we will put some weights on the left hand side first. So let's first put one weight at 14.5 centimeter away from the pivot point, and Let's put the second weight here at a distance of about 8.5 centimeter from the pivot point. Now let's try to balance it by placing the weight on the right hand side, such that we don't have to place the weight on the right hand side at exactly the same position as that of the left hand side. Let's try to find out some other configuration. But before we do that, let's try to calculate the torque because of these two weights. So first of all, we know that the torque because of this weight is 0.29, and if we calculate the torque at this point, which is at a distance of about 8.5 centimeter from this pivot point, so the torque value comes out to be 0.17 Newton meter. So if we add up these two torques, it would comes out to be 0.046 Newton meter. Now we have to apply a torque of 0.046 Newton meter on the right hand side to balance this beam. Now let's try to put some weight on the right hand side. Let's try to put it at a distance of 11.5 centimeter from this pivot point. So if we do that, if we calculate the torque on the right hand side, it would comes out to be 0.023 Newton meter. That's because if we multiply 11.5 centimeter or 0.115 meter multiplied by 0.2 Newton, so it would comes out to be 0.023 Newton meter. Remember, we have to apply a torque of 0.046 Newton meter here, which means that we still need another 0.023 Newton meter on the right hand side to balance it. So if we just take another weight and apply it at exactly the same location at 11.5 centimeter away from the pivot, so now you see that this beam has again been balanced, because the torque now on the right hand side is also 0.046 Newton meter, and if we sum up the torques on the left hand side and the right hand side, it would exactly cancel each other. So we arrive at the conclusion that when we balance a balanced scale, not only the masses on either side matters, but the distance of the masses from the pivot point also does matter. Thanks for watching.